Hello and welcome all my dear students. I am Dr. Sangeeta Bhattacharya and today I am going to start with lecture 2 of CS 302 data structures. In this lecture, we are going to see the following, we are going to continue with module 1 of our syllabus, and today we are going to see what is pseudocode, what is algorithm efficiency and analysis, and what are the order notations used for measuring the complexity of a loop. Now, if I talk about pseudocode, so in the last class, we have seen that when I talk about algorithm is specifically a sequence of steps which is used for measuring for carrying out a given problem. So if we are having an algorithm will be used for measuring for solving a given problem, and that will include certain number of steps. And we saw 5 characteristics of algorithms, namely input, output, finiteness, definiteness, and effectiveness. Now we are coming to pseudocode. Those pseudocode and algorithms are used sometimes interchangeably, but there is a slight difference between the two. And the difference is that when I'm talking about a pseudocode is basically, it represents the algorithm of a program in some natural languages and mathematical notations. So natural language, that is plain English language, will be used for expressing a program in terms of pseudocode, and some mathematical notations will be used. And how it is different from the programming language code, in the writing a pseudocode, we generally do not follow any kind of syntax. So we can write anything we want, but that should be understandable for the user. Let us see an example of finding out the maximum of 3 numbers. So such a program, if we are using pseudocode, we can write like this. So we can write program max of 3 numbers. Again, I am telling there is no way of writing, and we can write specifically anything we want, and that should be understandable for the user. So we can write read A. We can include a semicolon or we may not include a semicolon. That completely depends on the person who is writing the code. So read B. So because we are finding out the maximum of 3 numbers, so read C. And then these are the 3 numbers. Now see, in this case, we are not specifying whether A, B, C are integers, whether A, B, C are floats. We are not specifying anything. We are simply writing the logic. And then if A is greater than B, now if A is greater than B, what we do? We check then if, so you can use small case or you can use bigger case, whatever you want, is greater than C, then we can write print A. If this is not so, then we can write else print C. Now if A is not greater than B, then we are going to check for this condition if, so let's just make the font a little smaller. So if this is not the case, then what we will be checking is if B is greater than C. We have already done this programming in our programming C language program. So I think all of you can relate to that program. Print B else print C. Now, if A is not greater than B, so there is a indentation. Now remember, in case of pseudocode, indentation is very important. Well, in case of algorithms, indentation is not that much important because we are writing that in terms of steps. So the same program I will be writing down in terms of algorithm, and I think then it will be very clear to you. So end. So there will be an end if here to make understand here the if statement has ended. Then else if this is the case, then again there will be an end if here. So end if, and then the complete ended. So the last ended. Ultimately there is the end. Now see, in this program what we have written, in this program we have not written any steps 1, 2, 3, 4. This is the way in which we will be usually writing our algorithm, our program code, and that thing I have simply written here in terms of the algorithm, in terms of pseudocode. So this is the pseudocode where we are not following, so we have used some kind of natural language like read A, read B, read C. This is a natural language. Some kind of mathematical notations. Here we have used the relational operators greater than and greater than symbols, and then some if else. So this is the example of an pseudocode. Now, if the same thing we want to write in terms of algorithm, then what we have to write? So the first step in that case will be, so this is the algorithm, and I told that in case of algorithm, we have to always specify the input and the output. So the input in this case will be 3 numbers A, B, and C, and the output will be max of 3 numbers. And then we will be having our steps. And then we will be having our steps. So the first step is start. I told the algorithm always starts with the start symbol or the start statement. Then we will be writing find the largest of the numbers A and B and store the result in suppose max. So max is another variable. We are not specifying what kind of variable. And next what we will be doing, we will be finding the largest of max and C and store the result in maximum and store the result in maximum, and then we will be displaying maximum, and at the end there will be the end statement. So you can see the difference between the pseudocode. So if I talk about this is my pseudocode and this is my algorithm. So what is the difference if we see that algorithm is having my input statement and output statement, some sequential finite number of steps, and in this line, if find the largest of the numbers, Algorithm doesn't tell you how you can find out the largest of the numbers. It will only give you the steps. It depends on the programmer who is going to program this algorithm into code, how he will be finding out the largest number. Well, in case of a pseudocode, you see, we have already specified that how we can find out the largest of the two numbers by using the relational operator greater than. So this is the difference between the pseudocode and algorithm. Sometimes two types of algorithm approaches available. One is a top-down approach and the other is the bottom-up approach. Now what are they? Now if we look at this diagram, so this is a complex algorithm. This can also be thought about like a problem. So this can be thought about like a problem for which we have to design the algorithm. This problem can be divided into n number of sub-problems. So this modules, what we are actually having here, can be thought of as sub-problems. So this can be thought of as sub-problems. Sub-problems. One to n. So this is the problem, and this problem can be divided into a number of n number of sub-problems, which are this. Similarly, then the sub-problems can be further divided into sub-problems, and this continues until the size of each sub-problem becomes 1. This division may continue until the size of any sub-problem becomes 1. So if it becomes 1, that approach is known as divide and conquer approach, and there are many types of algorithm approaches. But what basically follows is we can either go from the top to bottom, that is we can have a problem at hand, we can divide it into sub-problems, and that sub-problems can be individually solved, and we can go down and that sub-problem, so this sub-problem can be solved. This sub-problem result can be used to solve the sub-problems and so on. So if we do that, it is known as a top-down approach. Now, what is the bottom-up approach? Rather than doing it in this manner, we first solve the sub-problems, and using the solution of the sub-problems, we solve the sub-problem. So this is the solution to the sub-problems are used for finding the solution of the sub-problem. So if it is like this, then it is known as a bottom-up approach. So the two approaches differ in the way we use the solutions of the sub-problems to reach the solution of the final problem. In case of top-down approach, the sub-problem solution is used to find out the solution for the sub-problems, where in case of bottom-up approach, the sub-problem solution is used for solving the sub-problem. And this is done in a from bottom to top. So the solutions of this level are used for finding the solution at this level. The solution at this level is found out for finding the solution of a higher level. Well, in case of top-down approach, the solution of the higher level is used for finding the solution of the lower level, and this process keeps on going. So this is known as a top-down and bottom-up approach. And these are and most of our algorithms either follow the top-down approach or it follows the bottom. Now, if we are talking about the algorithm efficiency, how can I measure the algorithm efficiency? Now, because we have done the C programming, we know that we can write number of programs using loops or without using loops. Now, if you are not using loop, it depends on the efficiency of the algorithm depends on the number of instructions it is having. Let me write a small program for making this understand. Suppose I write a small program for finding out the sum of two numbers. So what do I write? So I write a main first. And then I take two numbers, int a equals to 5 and b equals to 6. B equals to 6 and sum is equals to a plus b, and print if sum. If I talk about this simple program, here we have not used any kind of loop. So it depends on the number of instructions we are using for solving this program, and as many times we run this program, depending on your compiler load, it will be taking roughly an equal amount of time. So if the first time, if it is running for maybe 10 nanosecond, in the next time it may also run with maybe 11 or 12 nanosecond, depending on the compiler load what you are having on your CPU load. Rather not compiler load but CPU load. But roughly here the time taken will be constant. So we tell that in this case it will be a constant time taken because it is not depending on any factors. The instructions are plain and straightforward. So here in this case it depends on the number of instructions. But when we talk about loops, when the programs are having loops, then it usually depends on the number of loops and the running time of each loop. So if the program is having some loops, so specifically our loops are for loop, while loop and do while loop. So we are having three kinds of loops. So we are having for loop, we are having while loop, and we are having do while loop. So these are the three different kind of loops we are having. And in programming, if you observe, most of the time the loops used are for and while. So if we are using programs which are having loops, then it depends on how many number of for loops or while loop or do while loops we are using, and what is the running time of each of that. Loops, if we talk about it, there are three kinds of loops. One is a linear loop, one is logarithmic loop, and one is nested loop. Let us see one by one what is meant by each of this term. So first, let us talk about linear loop. So we can talk about a linear loop example like this. So now we are talking about linear loop. So in case of linear loop, if I write a code like this, so for I equals to 0, I less than 100, I plus plus, and then some statement block, some kind of statement block we are having. We don't know what is it. Some kind of statement block. How many times this loop is going to run? Now, if we look at this loop is going to run 100 times, because rather it is not going to run, this loop will be executed 100 times, because there are 0 to 99 plus 1. Once more this checking will be done for the statement for this checking whether I is less than 100 or not. Now within this statement blocks will be run how many times? It will be run for 100 times. So this loop is going to basically run for 100 times, because the statement block is going to run for 100 times, and this checking will be done for 101 times. Now, instead of 100, if this becomes 1000, then this is going to become 1000 and this is going to become 1000. Instead of 1000, now if it becomes n, so this is going to become n, and this is also going to become in. So this is a linear loop, where linear means where the increment is done on a defined gap, which is 1. So the gap is defined, which is 1, so it is increasing 1 by 1. So in this kind of cases, in case of linear loops, we can express this, for this particular example, we can express this in terms of a function f of n equals to n, where n is the number of iterations of the loop. So here, if it is 100, then f of 100 will be equals to, so this is a function in terms of the number of iterations. It will be 100. If it is 1000, it will be 1000, and so on. Now, instead of making it I plus plus, if I make it I plus 2. So let me just undo everything. Now, instead of writing it like I plus plus, if I make it for I equals to 0, I less than 100, I plus equals to 2, and then some statement block. Then in this case, how many times this loop is going to run? It is going to run for 100 by 2 times. So it is going to run for 100 by 2 times. That means if this is n, this is going to run for n by 2 times. That means we can express fn in terms of n by 2. So we see, what we see is that why it is called a linear loop, because here the incrementation, the value of I is changing in a linear fashion. Either it is changing by 1, or it is changing by 2, or it is, so the gappings are same. So in this case, the values will be 0, 1, 2, and then dot, 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 and 99. In this case, it will be something like 0, 2, 4, and then dot, 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 it will be 99. So in this case, we are reaching 99 in 50th time, but in this case, we are reaching it in the 100th time. So that means the difference is equivalent for the successive numbers in the range. So this is known as a linear. Now, if we talk about the logarithmic loop, so now we are talking about the logarithmic loop. So what happens in case of logarithmic loop? In this case, it does not change in a linear fashion. It changes in a logarithmic kind of loop. Let us see how. So again, let me write down a small program code. So for I equals to 0, I less than 100, so for I equals to 0, I less than 100, I into equals to 2, and then some statement block. Now in this case, we see that if we look at this nicely, here it is not changing in a linear fashion. How it is changing? So for the first value, if it is 0, this will be 1, not 0. So this will be 1. So for I equals to 1, so the first value, if it is 1, the next value will be 2, the next value will be 4, the next value will be 8, and it is changing in this manner because 1, then 1 into 2 is 2, 2 into 2 is 4, 4 into 2 is 8. So we see here the difference is not in a linear fashion, rather it is in terms of power, and if it is in terms of power, we can always express this. So how many times if I tell this loop will run, it will roughly run for log 100. If it is going to roughly run for log 100, that means the number of iterations will be equals to log 100. The same thing can be achieved if we are doing it by 2. So if it starts from I equals to, so if I equals to 100 and I is greater than equals to 1, then also it is going to roughly have the number of iterations to be log 100. In this case, and why? And what will be the base here? The base will be log 2. So log 2 with the base 2 is generally written as ln. So writing log 100 to the base 2 and writing ln 100 are one and the same thing. So if we look at this, so this is a logarithmic loop, and in this case, if instead of 100 it is n, then we can express it in terms of fn is equals to log of. So whenever the loop is incrementing or decrementing in terms of some power of 2, or in some power, not 2, but in some power, we can always express it in terms of log to the base that power. So here it is 2, that's why we have written log 100 to the base 2. If it is 3, we can write 3 and so on. So if I write like this, in this case, the base will be 2. And this is a very, very common example in case of algorithms if we study, where most of the logarithms are expressed in terms of 2. You will find that this is a very, very useful algorithmic complexity which is going to be used in most of our algorithms. Now, if I talk about nested loops, then nested loops can be of 3 types. So what is the first type? The first type is linear logarithmic loop. So there are 2 terms. So these 2 terms have been combined here and it has become linear logarithmic loop. And so what can be a possible example of it? Let us see. So if I tell for I equals to 0, I less than 10, I plus plus, and within that we are having a nested loop for j equals to 1, j less than 10, and j into equals to 2, and some statement block. Now we are not concerned about what is a statement block because we have seen in case of without loop, it will be a constant time. So constant time taken by the CPU. So if we look at this, so this first part is the linear loop. This second part is the logarithmic loop. So we know that instead of 10, so how many times it is going to run? So this particular program is going to have 10. So because this is the outer loop which is going to run for 10 times into log of 10, because this 10 is for this outer loop and this log of this is for the inner loop. Now, if we replace 10 with n, then we can simply write it like this. So if we replace it with n, we can simply write it like this. F of n is equals to n log. So we can simply write it like this. F of n is n log. So this is the linear logarithmic loop where the outer loop is running for n times and the inner loop is running for log n times. So the complexity or the efficiency can be measured at the multiplication of the number of times the outer loop is running into the number of times the inner loop is running. So this is linear logarithmic. Now let us look at the quadratic loop. This all types of loops we have already studied. Here we are just seeing how we can express the efficiency of those kind of loops in terms of some functions. So now we are coming to the quadratic loop. Now what is a quadratic loop? Now quadratic loop is very easy. So if I write for I equals to 0, I less than 10, I plus plus. And then if I write for I equals to, for j equals to 0, j less than 10, j plus plus. And then some statement block. Now we see this loop is going to run for, this is a quadratic loop because this loop is going to run for 10 times. This loop is also going to run for 10 times. Now we are not concerned about the loops, we are actually concerned about the number of times the statement block will be run. So this will be plus 1 and plus 1. So this will be how many times? This will be 10 into 10 times. So this inner statement blocks will be run for 10 into 10 times. So if we replace this tens with n, then we can write it like n into n. And in that case, Fn can be expressed in terms of n square. If there is one more loop here, so if we have another for loop here, so 3 consecutive for loops, it will become n cube. If you are having n number of loops, then it will become n to the power n. So this is known as quadratic, expressed in terms of power, where we can, so now you may ask me, ma'am, if this runs for 10 times and this runs for 20 times, then how can we express it? So basically it is n and this is m. Then in that case, if will be, we cannot write it, then it is as f of n because n is a simple term, but still mn can be considered to be approximately equal to n square. So suppose m is 10 and n is equals to 100. So m into n will be equals to 1000. And n square will be equals to something like 10,000. Now, if we are thinking about the CPU time, then this kind of small denomination changes doesn't matter, and that can be approximately. So as the value of this n and m increases, the time taken will be almost equivalent, and then we can approximately write it like this. We will be seeing that in the notations when we will be studying it. And the last one is a dependent quadratic loop. So I will just clear everything. So the last point which we are having is the dependent quadratic loop. So what is the example of a dependent quadratic loop? Let us see. So quadratic loop means definitely it will be a kind of, there will be a quadratic relationship, but how can we express that? So let us see this example. then for j equals to 0, j less than equals to I, and j plus plus, and then a statement block. Now why it is called as a dependent quadratic loop? Because here the inner loop is dependent on the value of the outer loop, j less than equals to I. Here the inner loop is dependent on the value of the outer loop. So if we look at this, how many times the outer loop will be running? So the outer loop will be running 1 plus 2, because for I equals to 0 it is going to run one time. Then for I equals to so if we are looking at this like this, so the outer loop is definitely going to run for 1. So 10 times, outer loop is going to run for 10 times. And the inner loop is going to run for how many times? For I equals to 0, the inner loop will be running once. For I equals to 1, inner loop is going to run 2 times. For I equals to 3, the inner loop is going to run for 3 times. Like this, for I equals to 9, the inner loop is going to run for 10 times. And this is approximately equals to 55. So in this case, we can express the inner loop iterates for how many number of times? So inner loop, so if the outer loop is iterating for, so if the outer loop is iterating for n times, the inner loop can be thought of repeating for n plus 1 by 2. N into n plus 1 by 2, so that we can see it from here. So why? Because 10 into 10 plus 1 by 2 is equals to 55. So we can express it in this time. So what will be the total complexity? The total complexity we have already seen. It is the complexity of outer loop into inner loop. So Fn can be expressed like that. In this case, Fn can be expressed n into n plus 1 by 2. So n is for the outer loop and this is for the inner loop, which is equals to n. So it is n square n plus 1 by 2. That's why it is called quadratic dependent quadratic loop. So quadratic because we have got a quadratic time n square, and because this inner loop is dependent on the outer loop, so it is a dependent. So with loops comes the complexity and the algorithm efficiency. With loops does not depend not only on the number of loops, but it also depends on what type of loops we are using. So if it is a linear loop, that means if the implementation is done in a linear fashion, then it is all right. If it is not done in a linear fashion, if it is done in a quadratic fashion, that is a nested loops, both the loops are running for the same number of times, then it will be in the terms of n square. Where if there is a dependent quadratic loop, then it will be in the terms of n square plus some other terms associated with it. So in this class, we have seen what is the difference between algorithm and pseudocode. What is algorithm? What are the different approaches for algorithm? And along with that, we have seen if we are having a program with some loops, how we can calculate the efficiency of that algorithm with loops and without loops in terms of n, where n is the number of iterations of the. In the next lecture, we will be seeing about the time and space complexity. We are going to continue with that time and space complexity and the different order notations which are used for calculating the complexity of the, and what is complexity and how we can calculate the complexity. Thank you very much.